In this video, we're going to be starting chapter 10, which is about harmonic motion, which we could also call oscillating or oscillatory motion. So far in Physics 106, we've talked about different kinds of motion of objects, balls being thrown and following parabolic arcs and things like that. But there's this whole class of motion that we haven't really discussed yet, and that is oscillations, or things moving back and forth, right? And this could be a lot of different things. This could be this could be something, like a mass hanging from a string, swinging back and forth like that, or it could be a point on a wheel going around in a circle. There are lots of different examples we see of this motion that repeats itself again and again over time. But so our definition of this motion is we have an object that's moving, for example, back and forth, or up and down, or left and right, or however we want to describe that, and returning to where it started. So, another example could be like we have a tree that's blowing in the wind, and as a result of that, it is swaying back and forth a little bit, right? So, returning to where it started, every once in a while, it ends up at the same point of this motion again. So if it's starts on the left and it blows to the right and sways back to the left, it has returned to where it started. As a visualization of this, I have a little toy or a little ornament, I don't know what you call it. So this is a little wooden person attached to a metal spring, and so we can hang this from the whiteboard as a demo. So the spring is stretchy but pretty. It has a low spring constant. We'll just say that. So we'll observe a couple things here. If I leave this, there is some nice equilibrium length the spring likes to be at that puts this person at some height. And if we give them some displacement, if we give them some initial displacement from this equilibrium position and let go, they oscillate in this up and down direction around this equilibrium point. So we'll hang on to him for a little bit. Okay, so we could say, let's think about ways that we could describe this motion. So one thing we could look at is, we know if they're starting at some point and undergoing this motion and returning to that point. So like we started at the bottom, we let go, they go up, they come back down, and they return to where we were at the bottom, like that. We can time how long that cycle takes, right? So ways we could describe the motion. And so this variable, that time, is called the period, and we use capital T for the period. This came up in our conical pendulum lab a while back, if you remember that. So the period is the time it takes to complete one cycle of the motion, or one oscillation, however you want to call it. So while this is bouncing up and down, one period is the time it takes it to go from here to here again. So from the bottom up and down to the bottom. It turns out that's also the same as the time it takes it to go. The time it takes it to go from the top down and back up to the top again. So no matter what point in the cycle you're measuring, the period is the time it takes to return to that same point in the cycle. Since this is the time, we measure this in seconds, just like we do any other time for SI units. Okay. It turns out it is convenient also to measure the frequency. So frequency and period are actually describing the same. There are different variables used to measure the same idea here. Hang on just a second. So our frequency, lowercase f, so our frequency is the number of completed cycles, or fractions of a cycle, I guess I should say. Completed cycles or fractions or parts of a cycle. In 1 second. So in other words, if we pulled this down, started a stopwatch, and measured how many oscillations we got in 1 second, right? So 1,000, maybe that was like 1.5 oscillations or something. The frequency is how many of these oscillations we're getting in 1 second. So our units of frequency are different than our units of period. These are different ideas. Our units of frequency are cycles per second. And this is an important enough idea, and this comes up so many times in so many different parts of physics. Frequency has its own unit, so 1 cycle per second is given the name of hertz, H-E-R-T-Z, and that is abbreviated capital H, lowercase z. So hertz are our units of frequency, but a hertz just means, 1 hertz just means something is happening once per second. 100 hertz means something is happening 100 times per second, 100 times in 1 second, and so on. If you have encountered hertz before, it's probably in the context of computer clock speeds, so how fast your computer processor executes instructions. That's measured in gigahertz, often billions of cycles per second. Radio frequencies for like AM radio and FM radio are in kilohertz or megahertz, so that's thousands or millions of cycles per second. There we're talking about oscillations of the radio waves of the electric and magnetic fields. You'll learn about that in Physics 107 if you take 107. Okay, so both of these are telling us something about how often this is oscillating up and down, right? Something with a very long period, something that goes up and down and takes a long time to do it, it is not going to get very far in 1 second. So it is going to have a low frequency. Similarly, something with a very short period, something that oscillates up and down very, very quickly, so there's a very short amount of time it takes to undergo one oscillation, in 1 second, it's going to complete a larger number of cycles, right? So it's going to have a higher frequency. Okay, so there is a mathematical relationship between period and frequency, and it is very simple. Our frequency is 1 over the period, or our period is 1 over the frequency. These are the same equation. So those are useful things to know. So of course, 1 over hertz is going to be 1 over seconds. So 1 over hertz is just seconds. That's in case you encountered that. All right. So those are our variables. So this is how we measure the time it takes our oscillation to happen. We also can talk about how big our oscillation is. So, in other words, for this little toy thing I have oscillating up and down over here, we can imagine it oscillating up and down a small amount, or we can imagine it oscillating up and down. I could have seen that coming. Or we could imagine it oscillating up and down a big amount. And this, I just want to do the big amount example, and then we can move on. Oscillating up and down a big amount, a bigger amount. Anyway, we'll go with that. So this size of the oscillation is what we call the amplitude. And depending on what the thing is that is oscillating, your amplitude can have different units. It could be a different thing you're measuring. So here, if we're looking at, the amplitude of this motion, that is like a distance in meters, right? How big it is oscillating, how far it is moving up and down, that is like a distance in meters. There are other oscillations where you might measure the amplitudes in some electrical units or magnetic units, or depends on what what kind of physics you're looking at. But in this class, our amplitude, the size of our oscillation, is generally going to be a length in meters. So for physics 106, this will be a length in meters. So if this thing is oscillating up and down, the amplitude is how far it is above and below its equilibrium position. So if it's oscillating like this, where we're measuring from its bottom here, when it's oscillating like this, and the bottom's going down to there, and the top's going up to here, this is not very symmetric, but the amplitude, these, as we will see if we do the numbers, these two parts should be the same, and the amplitude is this distance. So how far we are from the equilibrium position at the extremes. We'll deal with this in more mathematical detail later. For now, we can just know that the amplitude is the size of the oscillation. That's good enough.